Hello, welcome back to Math 332. This is the third video on Chapter 2 Determinants, and this is going to be the last video. So in the first video, we talk about the procedure of computing the determinants of a general n by n matrices by performing the cofactor expansion. And in the second video, we talk about the properties of a determinant, and in particular, we talk about the determinant for elementary matrices, which is right here. Okay, the elementary matrix for interchanging the rows is going to be -1. The determinant of the elementary matrices by multiplying a constant to that row is going to be k. And also remember that for legit row operation, this k is never 0 because we never multiply the entire row by 0. We never do that in the row operations. And so this k is non-zero. And we also look at the determinant of this row elementary matrix is going to be 1. And as you can see, the determinant of the elementary matrices are never 0, and it takes the value of either 1, -1, or some constant k. All right, so we're going to need that for our third video, because in our third video, we are going to look at this proof of the theorem 2.3.4. So before we look at the proof, let's make sure that we understand the statement of that theorem. Of this theorem. So it says that if you have two matrices, they are square matrices of the same size, I say they're n by n, then the determinant of the product of that two matrices is the same as the product of the determinant of that two matrices. All right, so we know that we don't have this kind of theorem. This is not true in general. So this kind of stuff is not true in general. But for product, we can actually do this. All right, so before we attempt the proof, there are a lot of stuff that we need to do. Well, the first thing that we need to do is we're going to look at this lemma. So lemma is basically a theorem. It's a mathematical fact. You still have to prove the lemma. The proof has to be as rigorous as how you prove theorem. The reason why we call it a lemma is kind of like this is usually something that is less significant the actual theorem, and it's kind of like the stepping stones that we use in order to achieve the real goal. The real goal here is to prove this, okay? But we cannot do it. It's just too difficult at the moment, and we'll be like, yeah, I cannot really do for the general matrix A. But for the matrix E, which is an elementary matrix, I can show that this is true. So that's what the statement of this lemma means. It means that if you have any general n by n matrix B, but the E is not any general matrices, this is an elementary matrix, this is elementary matrix, then this property will hold for this E here, this A here. Now we're not talking about any general A, but it hold for the elementary matrix E. So for elementary matrices, you can do that. Now, we are not going to attempt a general proof for this statement here. Instead, we are just going to show it in your homework, where you are asked to show that you have this kind of stuff, this kind of property for very specific elementary matrices. So in your homework, I'm asking you to show that this hold, but also not hold for all the general matrix E, not all the general elementary matrix E, but a very particular one, like this one, for example. So I control the size. I say that we are only looking at 3 by 3 matrices. And I also control the elementary matrices. I say that, okay, just work on this one. All right, so this one here is specifically specified to be the this matrix which you obtained by doing a row operations, single row operation from the identity matrix. And that row operations is obviously taking the third row, okay, and then changing the third row by taking the third row plus 3 times the first row. That is how we obtain that elementary matrix E. Hang on a second. My computer is overheated. Let's turn sound off. All right. Okay. So this is how we get this E, right? This is how we get this E by doing these row operations. So in this homework problem, they ask you to first compute EB. Now, you don't have to compute EB by using the definitions by doing this row multiply column. By now, you should remember that if you take elementary matrix, which is obtained from doing this row operation I, and if you hit it with the B on the left-hand side, you are basically doing that same row operation on B. So you're doing the same row operation on B. This is R3. R3 of B will change to R3 plus 3 times row 1. Okay, so you will get something that looks like this. So EB, if your B is like this, and your E is like this, your EB will be this, which means the third row of the B will change. And how does it change? It changes according to this rule. So we have that. So we have that. So that's how you compute EB. Now in the homework, you are asked to compute the determinant of EB. And you are asked to do that by doing a cofactor expansions along the third row. You're not doing anything else, just do it on the third row. And you are also asked not to multiply all the B because it's going to be a mess. So they want you to multiply. I want you to compute the determinant of EB by doing the cofactor expansion on the third row, and try not to multiply all the all the Bij. All right, you will see in a minute what I mean. Okay, because if you do that, it's going to be a mess. So this is our EB. So this is the third row. So we do a cofactor expansion on the third row. You will take the entries here, the coefficients here, and then this is the cofactor for this particular entries. And then you take these entries right here, okay, and then this is the cofactor for that particular entries. So these are cofactor expansion, nothing new. And then you take these entries here, okay, and you do the cofactor expansions, okay, right here. Now, what I mean is that do not multiply all the BI, all these entries here in the determinants is going to be very messy. So what I want you instead, what I want you to do instead is by taking these entries here, multiply this cofactor, and right here, and taking these entries here, multiply this cofactor, and right here, they are distributive because these are all numbers. Look at it, these are all numbers. So you can distribute to this, to write it like this, so on and so forth. So you do that for the second term and the third term also. Then you will get something that looks like this. Okay, so you get something that looks like this. Okay, so you distribute all that thing out. Now, by simply observing, you should be able to see that this part here is actually the determinant of this matrix. See that? So imagine that you are computing the determinant of this matrix by expanding along the third row. So you take this, okay, and then look at the cofactor expansions, which is right here. That's sign of the minor. Okay, so you have that here. And then if you look at this part here, okay, you look at this part here, and then look at the cofactor expansions along B32. I mean, the minor, the cofactor of B32, which is right here, the cofactor of B32. So what I'm saying is that if you look at this very carefully, if you look at this part here very carefully, this is actually the determinant of this matrix expand along the third row. Same thing here. If you look at, so same thing here, if you look at this part here, you can take out all the three, okay, and then you look at this part right here. This is actually the determinant of this matrix if you expand along the third row. So if you expand along the third row, okay, you will see that thing right here. Okay, expanding the third row, expanding along the third row. So from here, if you do it this way, I don't really have to multiply all the B out. So you can see that this whole thing here is actually this. All right, now, what is so special about rewriting it as this? Well, you will see that in these determinants, the first row and the third row are the same. So from the second video, you know that when they have two rows or even two columns, the same, so this determinant is immediately 0. So which means that the determinant of EB is just this, which is the same as determinant of B. So the second part of the problems asks you to find what is the determinant of EB. Well, you found that that determinant of EB turns out is actually just B. So you answer the second part. Now the third part says that compute the determinant of E. Well, this is, if you just compute this, you don't have to use any special theorem or whatever, because we are actually working on a specific example. So the determinant of E turns out to be 1. So it says that, so in this case, do we have this property? Do we have this property? And the answer is yes, because the determinant of EB according to our computation is B. And since determinant of E according to our computation is 1, so I can write these terms here like this. Determinant of EB is determinant of B, just like what we have here. But then I put a 1 in front of it, and the 1 is actually the determinant of E. So in this case, the determinant of EB is really the determinant of E times determinant of B. So we have shown in this single example right here, in this particular case, very particular, right? Only referring to this, we do have this relationship hold. All right. So how do you prove this in general? Well, it's not difficult. Once you see this, you know how to actually proceed. It's just that in general, if you want to show this thing in general, you have to do it in n by n case. So you cannot write like that. You have to use the notation A11, all that thing. It's just a little bit messy to write all this thing out. But the idea is the same. So you cannot do it on this terms. You will be like some kind of K of this. So it's like all the notation is a little bit messy. But the main idea, you can kind of see it from the proof that it holds. This relationship hold for this particular elementary matrix, but it will hold for all the elementary matrices that looks like this. So in your homework, you have you will have to investigate this for 3 types of elementary matrices. And so we're not claiming that this is a proof. We're just claiming that by doing that, you will understand why lemma 2.3.2 is true. So now we can, we're not proving it in general, but this is a true fact. So now we're going to use this as a fact to see whether or not we can get theorem 2.3.4. Now, but before we even attempt to do that, let's kind of like take a detour by looking at another very important theorem, which is this one. Okay, so it's this one right here. Now, this theorem, 2.3.3, which is on page 120, says that if you have a square matrix, and if the square matrix is invertible, then the determinant of A will not equal to 0. You say that if you have an invertible matrix, then the determinant of that matrix cannot be equal to 0. It say the converse is also true, because this is if and only if, which means that if you have a matrix with determinant not equal to 0, that matrix must be invertible. So this is something that we say in mathematics, some very nice characteristic, some theorem, a very nice theorem that characterize the property of A being invertible, which means that A being invertible, then you must have this, you have this, A must be invertible. This go both ways. So a square matrix is invertible if and only if the determinant is not equal to 0. So there's no ambiguity. How do you determine whether our matrix is invertible or not? You look at the determinant and see whether or not it's 0 or non-zero. That is the one that characterizes the matrix being invertible. So that's a very nice characterization of A being invertible. How do we characterize it? We look at the determinant and see whether or not it's equal to 0. Okay, so let's look at the proof. Okay, so since it's 2 directions, so let's first look at this direction, which says that now, okay, the hypothesis is that A is being invertible. Okay, so this is what you're assuming. What do you want to show? So what you want to show is that with this as your hypothesis, your determinant of A must be something that is not 0. Okay, so how do we do that? Now, so remember that A being invertible, meaning that you can actually row reduce it all the way to the identity matrix. Remember that the video on how to obtain the inverse matrix by doing row reductions. So we have something that's A, we set this thing up like that, and then we row reduce. If you can reduce this to identity matrix, then whatever you have here, that's the inverse, right? So saying A is invertible is saying that you can actually row reduce A to the identity matrix. Now we also know that instead of saying that it is row reduced, it is equivalent to saying that there exist all these elementary matrices, such that if you multiply all these elementary matrices on the left of A, you are basically doing the row reductions. Okay, we talked about this in detail last time. So saying that A is invertible is the same as saying that A can be row reduced to the identity matrix, which is the same as saying that you can take all these elementary matrices, multiply it with A on the left hand side, and you can turn it to the identity matrix. Now here is how we apply the lemma. So if we take the determinant of this matrix and we take the determinant of this matrix, so obviously the determinant of the identity matrix is 1, and here if you break this thing apart like this, then you will see that this is an elementary matrix multiply another matrix. According to the lemma, we can split this. So for this particular elementary matrix multiply with another matrix, we can split this as the determinant of this elementary matrix multiply the determinant of this some other matrices, right? Okay, and this is equal to 1. And we can apply this multiple times. When we are done with this, okay, when we are done with this, we're now concentrating on this. And again, we split this. And then we split this again. We split this again. So eventually, you can break everything out. You can break everything up and write it like this. Okay, now this is 1, obviously non-zero, and these are the elementary matrices and their determinant, and we know that the determinant of elementary matrices are never equal to 0, so these are actually non-zero. So if you have non-zero multiply the determinant of a equal to 1, well, the determinant of a must be also non-zero. So that is what we try to prove right here. So we have finished the proof for one of for these directions. So we start with the hypothesis that a is invertible, and then therefore that the determinant of a is not equal to 0. That's the proof. All right, now let's look at how we prove the converse of the theorem. So now if we want to go this directions, this will be our assumption now. This part here will be our assumptions. If you want to go this way, this is our assumption. So our assumption is that determinant of a is not 0. What do we want to show is that with that, your matrix A has to be invertible. So this is what we want to show. A is invertible. So how do you show that? Well, one way is to imagine you take the matrix A and you start to row reduce it all the way to RREF. This is RREF of A. The real REF, the row reduced echelon form, the reduced row echelon form, which means that if you have a pivot, everything above the pivot has to be 0, everything below the pivot has to be 0. Now, so assume that we're doing this. We are row reducing it all the way to the RREF of A, which we call it R. So as we discussed before, it is equivalent of saying that there exist elementary matrices such that R is equals to the product of all these matrices. Okay, so saying that A, I'm not saying that this is I yet, I'm just saying that this is a row reduced echelon form of A. Now, so once we have this, we apply the determinant and we apply the lemma also. So same argument as we have before, because these are elementary matrices, we can split all of them out like that. Okay, and then we have that. Now, the hypothesis says that this is non-zero. We know that determinants of all these elementary matrices are also non-zero. So therefore, the determinant of this RREF of A is also non-zero. Okay, which is here. The determinant of this RREF of A is non-zero. Now, well, this part here, you have to give it a little bit thought. If not, you can read the proof in theorem 1.4.3, which says that if you have RREF of a matrix, this is a real RREF, n by n though, otherwise it's not true. So it's n by n matrix being an RREF of a particular matrix with determinant non-zero. This matrix R here has no choice but to be I. Okay, give it a little bit more thought and you will see why. If not, you can actually also look at the proof of theorem 1.4.3, saying that n by n square matrix RREF determinant non-zero, it has to be I, which means that with this hypothesis that the determinant of the matrix is not equal to 0, and if you imagine they are doing the row reduction, you actually can row reduce all the way to I. You don't have a choice that R has to be I. So why is this invertible? Same thing, right? Remember, if you can row reduce it to I, whatever you have here, this is the inverse. This is the inverse of A. So if you can show that the row reduction can actually be carried through all the ways to make this whole thing I, then therefore the matrix A is invertible. So that's the second part of the proof, showing that with this hypothesis, your A can row reduce to I, which means A is invertible. So therefore you have proof to both directions, and therefore you have established these very important characterizations for which matrix is being invertible or not. All right, so let's pause and think for a minute. So now we have a very important theorem which tells us when a matrix is invertible. We look at the determinant. All right, so that's that. Now with this, we are now ready to prove theorem 2.3.4. All right. So we are now talking about a general matrix A now. We're not just talking about the elementary matrices. So how do we do that? So the proof, okay, will be separated into two separate cases. First one is we are assuming that A is non-invertible and try to show that if A is non-invertible, we have this. All right, so how do we do that? So suppose A is non-invertible. We know from the homework problem using nothing but the definitions and the proof called proof by contradiction. Using nothing but that, we shows that if A is non-invertible, then AB is also non-invertible. Okay, now, so by the theorem that we have just seen, if A is non-invertible, then the determinant of A cannot be not zero. It has to be zero. So also AB, okay, if it is also non-invertible, then the determinant of AB also has to be zero. So which means that in this case, the case one here, where A is non-invertible, therefore AB non-invertible, we have this equality hold. It holds trivially though, because this is actually a zero. So this is actually a zero, and this is actually a zero. So you're basically saying that zero is zero multiplied something. Okay, so that's actually what it said. So you have it anyway. You have it when A is non-invertible. Okay, so when A is non-invertible, this relationship trivially hold. But what happens when A is invertible, right? So you have to prove both of the cases in order to prove for all cases, because all the matrices is either invertible or not invertible, right? So for non-invertible, we have it. For invertible, what happens? Well, when it's invertible, same thing as before. There exists all the elementary matrices such that you can row reduce A to I. That's basically what it say right here. And now, if you apply the determinants, if you try to compute the determinant of A, B with A equal to that, so instead of writing out the A, you write this. Okay, so the determinant of AB will be computing the determinant of all this product of elementary matrices and B. So again, the lemma says that if all these elementary matrices, you can break them into this. Okay, so you can write it as the product of all these determinants, and then you have determinant of B. And this part here, and this part here, right here, this is actually determinant of A, because A is like that, right? So your determinant of A is equals to the determinant of all this, and these are all elementary matrices. So again, you can split them apart, and you have this. So everything that you see right here in this box is actually A, determinant of A. So this is this, and therefore we have shown that the determinants of the product AB is the same as the product of determinant of A and B when the case that the A is invertible. So you actually have shown the case where A is non-invertible. You show the case where A is invertible. So therefore, this relationship actually hold for all cases, for all possible A that you can think of. Therefore, this is the proof of this theorem. Okay? All right. So that's a proof of theorem 2.3.4. Now, before we move on, I have comments to make. So you remember the this particular facts that we use here in case one. A is non-invertible implies that AB is also non-invertible. We actually asked you to show. I actually asked you to show that in your homework by using nothing more than the definition of invertibility, and also the concept of proof by contradiction. Now, some of the students in class have seen determinant before, and so this is how the argument go. It says that we want you to show this, then they are actually invoking the determinant. They will say something like this: determinant of AB is equal to determinant of A times determinant of B because of this theorem, and because A is non-invertible, so therefore the determinant of A is 0. So hence 0 multiplied this is also 0. So therefore by that theorem 2.3.3 again, we'll say that being determinant being 0, meaning that AB is non-invertible, which means that they have shown that A not invertible implies AB not invertible. First of all, this doesn't follow the instruction of the homework. Homework asks you to use nothing but the definitions. So if you use this, you will be in trouble, because you can see in this proof right here, you are actually using that as a fact. So what I'm saying is that, so if you're asked to prove statement A, you're asked to prove statement B, but you're using A to prove statement B, and then you use statement B to prove statement A. So you're running your argument in loops. So you're running your argument in loops. So here, so if you're using this kind of, if you're using this kind of argument, okay, to show that A not invertible means that AB not invertible, but you also use it here in the proof, okay, then it's going to be problematic. So that's the reason why in your homework I'm asking you to use nothing more than the definition. So if you are not using anything that is fancy involving determinants, so this facts is independently can be verified, can be proved by doing by using nothing more than the definitions, then it will be fine. So this is going to be okay. This is actually coming from the homework, and then once with that, we can actually show all this thing true. So we don't have to run into a logical problem, which is like in the proof involve a proof, which involves the things that we want to prove. All right, so that's just a little bit comment. One final thing is Cramer rule. So Cramer rule is a very nice way of solving a system of linear equations, same thing as the one that we always wanted to solve, which is, say, suppose you have a matrix A, this is 3 variable, and this is the B, and we want to find x1, x2, and x3. Now we know that we can always do that using a row reduction method, Gauss-Jordan elimination and all that, but we can also use determinants to do that. So what Cramer rule says is that in order to compute x1, so you take the original coefficient matrix, x1, so you want to compute x1, you take the first column of this matrix A, take it out, okay, and substitute it with B. Take it out and substitute it with B, only the first column, the rest stay the same. So you can see that the rest stay the same, but the first column of matrix A is now being replaced by B. So if you compute this determinant, and then divided by determinant of A, obviously this has to be, this only works when the determinant of A is non-zero. This is also one restriction for Cramer rule. Cramer rule only works when the determinant of A is not equal to 0, which means that we do have unique solutions. Otherwise, you cannot use that. So the determinant of A, you divide that, which is according to the computations, which is this, then you get the x1. So in order to get x2, you take the second column out of the matrix A and substitute it with that values in the vector B. So this is what happened. The rest stay the same. Compute this determinant and then divide it by determinant of A. That's how you get x2. That's what Cramer rule say. Same thing. Now you know. Take the third column out, put the B inside here and compute. You get x3. That's you might wonder why do we want to have a Cramer rule, use the different methods to compute x1, x2, and x3 instead of using the row reduction. Now this is nicer in the sense that we have a formula for x1. If not, try to imagine if your friend asks you what is x1, you cannot tell the persons whether or not how do you actually find the x1. You'll be like, we'll have to row reduce to RREF, then we will see x1. So you actually have to describe a process. For this one, you don't have to describe a process. You will be like, just compute this. So this is like an easy way to write down the solution of x1, x2, and x3 when the solution exists and unique. Okay, but again, though, the row reduction method is much more general. It can handle any type of situation when you have no solutions, infinitely many solutions, or whatever. But for the when you have a square system, you have a square matrix where the determinant is defined and the solution is unique, you can actually apply Cramer rule this way. Okay, how do you prove Cramer rule? So I'm going to give you an alternate proof, which is very easy. Once you see it, you will know what to do, which is different from the proof given in the book because we didn't talk about those ideas. So we are not going to use those proof in the book. So the proof for Cramer rule is actually very easy. And actually, this is also something you can remember very easily. So instead of writing this system, we can write it this way. So remember, try not to multiply everything out. Try to remember the column pictures in matrix multiplications. So remember that, for example, right here, this means that you take 0 of this first column plus 1 of this second column, and then take 0 of this third column and put it together in these positions. That is where you get A12, A22, A32. All right, so same thing. If you look at this part here, so this says that you take 0 of this column, 0 of this column, plus 1 of this column. So obviously you get this. All right. And how about this one here? So this one here says that you take A11, A21, A31, multiply x1 plus A12, A22, A32, multiply x2, and then you get A13, A23, A33, and then multiply x3, and then put it right here. And that is exactly what this thing is about, right? So if you do this, if you take x1, x2, x3 as a column and put it inside here, you will get B1, B1, B2, and B3. So try to review your matrix multiplication using the column pictures, and you will see very clearly that this is true. So now there are 3 by 3, 3 by 3, 3 by 3 square matrices. We can apply the determinant. So once we apply the determinant, this is nothing but this. And because we spent so much time proving that theorem, that determinant of A and determinant of B, you can split it into this. So now we're going to apply it right here. So now you have two matrices. So we have the determinant of the product of these two matrices is written as the determinant of this matrix and determinant of this matrix. Now this is nothing but determinant of A, and if you compute the determinant for this guy right here, this is a lower triangular matrix. Just take the product of all the diagonal, you see this. So x1 will be nothing but this. All right, so you apply the same principle. You will see that this matrix here will have to multiply this matrix to get this. And now if you compute the determinant for the things on the left hand side, you have this. Compute the determinant on the right hand side, you have that. This determinant, even though this is not upper triangular or lower triangle or diagonal, this determinant is also very easy to compute. There are so many zeros here. So you can exploit that and you will get that x2 as well. And finally, so you get that. And finally, if you multiply all this thing out together like this, you will see that you have that. So apply the determinant on the left-hand side, split it into 2. And then this is the determinants, divide that by determinant A, and you get that x3. So the proof is pretty easy once you know this is the techniques. This is like the trick. Okay, so this is like how we write all this thing out so that we can apply the determinant, so that we can split the determinant. And then we move things around and we get that. So that's called Cramer rule. It's easy to apply if you want to compute determinant. And this is like nicer in the sense that we have a general formula for that instead of just telling people to do a row reduction. Okay, so that's all you need to know for the test on Thursday. And I will see you on Tuesday then. That's it.